Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. A curious divergence characterized the intellectual currents of the mid-20th century. Within the austere halls of pure mathematics, differential geometers pursued questions of intrinsic beauty and logical necessity, seeking the most perfect, canonical forms that abstract spaces could assume. Their world was one of manifolds, curvature, and topology, a universe of thought governed by internal consistency and aesthetic elegance. In a parallel, seemingly distant realm, theoretical physicists were embarking on a speculative and audacious journey. They were sketching the preliminary outlines of what would become string theory, a framework that promised a unified description of all physical forces, but at a cost. The universe it described possessed a startling 10 dimensions. The challenge for physics was immense. Where were these extra dimensions, and what mathematical form could they possibly take to remain hidden from our four-dimensional perception while upholding the theory's delicate symmetries? For a time, these two grand quests proceeded along separate trajectories, their languages and objectives appearing utterly distinct. The geometer's question found its most refined expression in a 1954 conjecture by Eugenio Calabi. His proposition was a deep and subtle one, concerning a special class of spaces known as compact Calabi manifolds. These are realms where the rigidity of complex analysis, the smoothness of differential geometry, and the global properties of topology merge with extraordinary grace. Calabi focused on a particular geometric invariant, the Ricci curvature, which measures how the volume of a space locally expands or contracts relative to flat Euclidean space. A space where this curvature vanishes everywhere is called Ricci flat. It represents a kind of gravitational equilibrium, a perfect balance. Calabi proposed that for any compact Calabi manifold satisfying a certain topological prerequisite, the vanishing of its first Chern class, a unique Ricci flat metric must exist. This was a breathtaking assertion, linking a global topological condition, something you could compute algebraically, to the existence of a specific, ideal geometric structure, which would have to be found by solving a formidable differential equation. For over 2 decades, the conjecture stood as a monumental challenge, a siren call to the world's leading geometers. Meanwhile, physicists wrestling with the dimensional problem of string theory faced a complementary puzzle. The theory's consistency required that the 6 extra, unseen spatial dimensions be curled up or compactified into a tiny, stable manifold. Furthermore, a central physical principle, an elegant symmetry between matter particles and force-carrying particles known as supersymmetry, had to be preserved in the transition from 10 dimensions to 4. When translated into the language of geometry, this physical requirement became a concrete mathematical constraint. The 6-dimensional compact space they were looking for needed to admit a metric with 0 Ricci curvature. Physicists were, in essence, searching the cosmos of mathematical possibilities for a Ricci flat compact manifold. Yet they possessed little assurance that such objects were plentiful, or that they even existed in the required forms. They had a physical need with an uncertain mathematical supply. The resolution of both dilemmas arrived through the singular effort of Shing-Tung Yau. His approach to the Calabi conjecture was a masterpiece of geometric analysis, a field that leverages the power of calculus and differential equations to uncover the secrets of geometric spaces. Yau reformulated Calabi's geometric assertion into a highly non-linear partial differential equation of a type known as a complex Monge-Ampère equation. The sheer complexity of this equation made finding a direct, explicit solution a practical impossibility. The path forward lay in proving that a solution had to exist, even if one could never write it down. To achieve this, Yau employed the continuity method, a powerful strategy for solving difficult equations. The method involves starting with a simpler solvable version of the problem and continuously deforming it into the hard problem of interest. The core challenge is to demonstrate that a well-behaved solution persists throughout this entire deformation, without breaking down or flying off to infinity. This is where Yau's technical brilliance came to the fore. He embarked on the monumental task of establishing a series of a priori estimates. These are intricate analytical inequalities that act as conceptual guardrails, boxing in the family of possible solutions and guaranteeing their smoothness and boundedness. Yau had to control the solution itself, its first derivatives, its second derivatives, and ultimately its third derivatives. Each step up this ladder of estimates presented a more profound difficulty than the last. The calculations were famously arduous, filling hundreds of pages with dense technical arguments that pushed the frontiers of the theory of partial differential equations. He was, in effect, constructing an elaborate analytical cage, one powerful enough to trap a solution to one of the most stubborn equations in geometry. After years of intense labor, culminating in 1976, he succeeded. He established the final, crucial estimate, completing a proof that affirmed Calabi's two-decade-old vision. The impact was immediate and transformative. Yau's proof guaranteed the existence of a vast class of compact, Ricci-flat Kähler manifolds. Almost as soon as the result was announced, physicists recognized its profound significance. A team comprising Philip Candelas, Gary Horowitz, Andrew Strominger, and Edward Witten demonstrated that these very spaces, soon to be christened Calabi-Yau manifolds, were the perfect candidates for the compactified dimensions of string theory. They provided the precise geometric arenas in which the extra 6 dimensions could curl up while preserving the all-important supersymmetry. A bridge between the most abstract mathematics and the most ambitious physics had been built, almost overnight. This fusion created a vibrant new discipline, connecting algebraic geometry and string theory in a dialogue that continues to yield deep insights into both fields. The methods Yau pioneered to tame the Monge-Ampere equation became fundamental tools in the geometer's arsenal, altering the very way mathematicians approach problems at the interface of analysis and geometry. By providing the mathematical bedrock for string compactification, Yau's work gave physicists a concrete language to describe the geometry of hidden worlds. The shape of these Calabi-Yau spaces, it was theorized, could determine the fundamental constants of nature and the spectrum of elementary particles we observe in our own large-scale universe. The same intellectual power that carved out these hidden microscopic universes would soon be directed towards the largest scales imaginable, confronting a foundational question within Einstein's own description of gravity. The stability of space-time itself, a principle at the heart of general relativity, awaited a rigorous geometric defense. This defense was essential for the logical coherence of Einstein's universe. The theory of general relativity, while describing the grand cosmic dance of planets and galaxies with stunning accuracy, rested upon certain foundational assumptions about the nature of spacetime. One of the most elementary, almost primal, of these assumptions is that of stability. A physical system left to its own devices should settle into a state of minimum energy. It should possess a ground state. For gravity, this translates to a question about mass. The total mass, or more accurately, the total mass energy of an isolated gravitational system, such as a star or a galaxy, ought to be positive. A universe where systems could possess negative total mass would be a pathological one. Such an object could, in principle, radiate away an infinite amount of positive energy, thereby decreasing its own mass to negative infinity, a process that would violate every intuition about physical reality. While this principle of positive mass energy seems self-evident, proving it from the labyrinthine and highly nonlinear Einstein field equations was a formidable challenge that had stood for decades. The problem required a precise mathematical formulation. For an isolated system in a spacetime that becomes flat far away from the source of gravity, an asymptotically flat spacetime, the total mass is defined by a quantity known as the ADM mass, named for its creators Arnowit, Deser, and Misner. This ADM mass is a delicate measurement, calculated from the subtle ways the geometry of spacetime deviates from perfect flatness at a great distance. The central question became a purely mathematical one, albeit with profound physical implications. Can one prove that the ADM mass is always greater than or equal to zero, provided that the local matter and energy content everywhere is itself non-negative? This latter condition, known as the dominant energy condition, translates in the language of geometry to a statement about the curvature of spacetime, specifically that a quantity called the scalar curvature must be non-negative. The problem was a linchpin for the entire theory. Without a proof, the mathematical consistency of general relativity remained under a cloud of doubt. Here the geometric intuition that Shing-Tung Yau had honed in the abstract landscapes of Calabi manifolds found a new cosmological canvas. In a landmark collaboration with his former student Richard Schoen, Yau devised a proof of the positive mass theorem that was breathtaking in its geometric purity and power. Earlier approaches had yielded results for specific configurations of spacetime or under more restrictive assumptions. The Schoen-Yau argument, however, was a masterclass in geometric analysis, transforming a problem in physics into a profound statement about the topology and geometry of three-dimensional spaces. Their strategy was one of elegant, indirect reasoning, a proof by contradiction. They began by assuming the opposite of what they wished to prove. Let us suppose, they said, that an asymptotically flat three-dimensional manifold with non-negative scalar curvature exists, and its total ADM mass is negative. Their next step was the crucial innovation. They demonstrated that this single assumption, a negative total mass, has a dramatic geometric consequence. It forces the existence of a very special kind of surface within the manifold, a compact, two-dimensional minimal surface. A minimal surface is the higher dimensional analog of a soap film. It is a surface that at every point curves in such a way as to locally minimize its area. Think of a soap bubble stretched across a wire frame. The shimmering film contorts itself into the shape with the least possible surface area for that boundary. Schoen and Yau showed that a universe with negative total mass would, paradoxically, be compelled to contain such an area-minimizing bubble, a closed surface with no boundary, floating within it. The existence of this surface became the hinge of the entire argument. Having established that negative mass implies a compact minimal surface, Schoen and Yau then turned to prove that such a surface is in fact an impossibility within a manifold that has non-negative scalar curvature. This part of the proof is a technical tour de force, relying on a deep analysis of what is called the second variation of the area functional. This is a mathematical tool that determines whether a minimal surface is stable. A stable minimal surface is one that truly minimizes area, much like a ball resting at the bottom of a valley. An unstable one is like a ball balanced precariously on a hilltop. Any tiny perturbation will cause it to roll off and decrease its area. Schoen and Yau derived a formula, now known as the Schoen-Yau stability inequality, which relates the stability of the minimal surface to the surrounding geometry. Their formula revealed that in a space where the scalar curvature is non-negative, any such compact minimal surface would have to be unstable. The pieces of the logical puzzle then fell perfectly into place. The assumption of negative mass implied the existence of a stable, compact, minimal surface, yet the physical condition of non-negative local energy, expressed as non-negative scalar curvature, made the existence of that very same stable surface a geometric impossibility. This is a classic reductio ad absurdum. The two conclusions are in direct conflict, meaning the initial premise must be false. The total ADM mass of the system cannot be negative. It must be zero or positive, securing the stability of Einstein's spacetime on a rigorous mathematical foundation. The proof was a triumph, celebrated for its depth and its beautiful fusion of differential geometry and partial differential equations. The implications of the Shing-Tung Yau proof extended far beyond the immediate result. It armed mathematical physicists with a powerful new paradigm. The technique of using minimal surfaces as geometric probes to deduce global properties of a spacetime, like its total mass, became a cornerstone of modern geometric analysis. It opened the door to solving a host of related problems in general relativity and differential geometry, including subsequent generalizations of the positive mass theorem to higher dimensions and different physical contexts. The successful application of deep geometric principles to the cosmos affirmed an intellectual approach of immense power, one that viewed the equations of physics as statements about the shape of reality. This very paradigm, connecting abstract geometry to physical theory, would soon find itself at the heart of an even more mysterious and consequential dialogue emerging from the world of strings. The implications of the Shing-Tung Yau proof extended far beyond the immediate result. It armed mathematical physicists with a powerful new paradigm. The technique of using minimal surfaces as geometric probes to deduce global properties of a spacetime, like its total mass, became a cornerstone of modern geometric analysis. It opened the door to solving a host of related problems in general relativity and differential geometry, including subsequent generalizations of the positive mass theorem to higher dimensions and different physical contexts. The successful application of deep geometric principles to the cosmos affirmed an intellectual approach of immense power, one that viewed the equations of physics as statements about the shape of reality. This very paradigm, connecting abstract geometry to physical theory, would soon find itself at the heart of an even more mysterious and consequential dialogue emerging from the world of strings. That new dialogue began in the late 1980s, emanating from the speculative frontiers of string theory. In their quest for a unified theory of everything, physicists postulated a universe with extra hidden spatial dimensions. To reconcile this 10-dimensional picture with our perceived 4-dimensional reality, they proposed that these extra dimensions were curled up or compactified into an infinitesimally small complex space. The geometry of this hidden space was paramount. Its shape would dictate the fundamental laws of physics, the spectrum of elementary particles, and the constants of nature we observe. The leading candidates for these compactification spaces were the very Calabi manifolds, whose existence Yau had proven. His work had provided the stage upon which this new theoretical physics would unfold. Then a discovery of stunning strangeness emerged from the physicists' calculations. They found pairs of Calabi manifolds that were, from a mathematical perspective, entirely distinct. They possessed different topological invariants, such as their Betti numbers, meaning their fundamental whole structures were dissimilar. A geometer would look at the two and declare them to be different worlds. Yet, when physicists performed their string theory computations on these distinct manifolds, they arrived at identical physical theories. The particle spectra, the interaction strengths, the entire physical content was the same. It was as if two completely different architectural blueprints produced the exact same building, down to the last fixture. This phenomenon, dubbed mirror symmetry, was a computational godsend for physicists, allowing them to perform a difficult calculation on one manifold by translating it into an easier one on its mirror partner. For mathematicians, it was a profound and unsettling mystery. It suggested a deep, hidden equivalence, a duality in the world of geometry that was completely invisible to their existing tools. Yau, as the central figure in the study of these manifolds, immediately recognized the depth of the challenge. He saw the physicists' empirical finding as a message from a deeper level of mathematical reality. He became a crucial conduit, organizing a series of influential conferences that brought the two cultures of theoretical physics and pure geometry into intense, often difficult, conversation. His goal was to translate the physicist's intuition into a rigorous mathematical framework. This effort culminated in one of the most influential conjectures of modern mathematics. In collaboration with the physicists Andrew Strominger and Eric Zaslow, he proposed what is now known as the SY-ZIZ conjecture. The conjecture offered a concrete geometric explanation for the mirror mystery. It posited that mirror pairs of Calabi manifolds should share a special underlying structure. Each manifold, it proposed, could be decomposed into a family of lower dimensional shapes called special Lagrangian tori, a structure known as a torus fibration. A torus is the geometric shape of a donut. The SY-ZIZ conjecture stated that the mirror of a Calabi manifold is constructed by performing a specific dual operation on this torus fibration. In essence, the geometry of one manifold's fibers is transformed into the geometry of the other manifold's base, and vice versa. This elegant idea converted a physical duality into a precise geometric program. It provided a potential roadmap for proving mirror symmetry, transforming it from a collection of surprising physical calculations into a profound statement about the hidden symmetries within geometry itself. The conjecture remains a central pillar of research, guiding mathematicians as they continue to unravel the intricate tapestry connecting geometry and the quantum world. Parallel to his deep engagement with the frontiers of theoretical physics, another defining feature of Yau's later career began to take shape, a monumental effort in institution building. Having reached the pinnacle of the Western academic world, he turned his attention eastward, toward the mathematical landscape of his native China. He perceived an enormous reservoir of intellectual talent there, a potential that he felt was constrained by a lack of institutional infrastructure capable of nurturing it to a world-class standard. His vision was to create centers of excellence that would function as engines of mathematical progress, operating at the highest international level on Chinese soil. Leveraging his global stature and formidable fundraising capabilities, Yau embarked on an ambitious architectural project of a different kind. He founded and directed a series of elite research institutes, beginning with the Morningside Center of Mathematics at the Chinese University of Hong Kong, and later the Yau Mathematical Sciences Center at Tsinghua University in Beijing, among others. His approach was a direct importation of the structures and, more importantly, the exacting standards of the world's leading research centers. He recruited a powerful mix of top international scholars and leading expatriate Chinese mathematicians, creating an environment that was both a homecoming and a new frontier. The philosophy behind these centers was one of total immersion in the global mathematical conversation. They were designed as crucibles combining advanced graduate training with frontline research. Seminars, workshops, and long-term visiting programs ensured a constant flow of new ideas and international collaboration. The atmosphere was deliberately intense, fostering a culture of high ambition and rigorous intellectual competition. For the students and young researchers, it was an unparalleled opportunity to learn from the masters and to be pushed to their absolute limits. Yau's work here was that of a cultivator, building the ecosystem necessary for a new generation of mathematicians to flourish. Through these centers, he sought to create a self-sustaining tradition of excellence, ensuring that the future of mathematical discovery would be a truly global enterprise. This grand project, building the human and institutional architecture for future breakthroughs, reveals a vision for mathematics that encompasses both the discovery of abstract truths and the creation of the communities dedicated to pursuing them. This immense effort in building the human and institutional architecture for discovery served a profound intellectual purpose. The centers and seminars were the physical embodiment of a conceptual revolution Yau was spearheading. His life's work, viewed from a sufficient distance, reveals a coherent and ambitious project, the elevation of geometric analysis into a dominant language of modern mathematics and theoretical physics. While the solutions to the Calabi conjecture and the positive mass theorem stand as monumental achievements, his ultimate contribution is perhaps the establishment of this field itself as the primary arena where the deepest questions of shape and space are resolved. He envisioned, and then constructed, a powerful bridge between the abstract world of pure geometry and the concrete demands of physical reality, a bridge built with the rigorous tools of partial differential equations. This vision is exemplified by his role in shaping what became known as the Yortian-Donaldson conjecture. The problem at its heart is fundamental to complex geometry, determining the precise conditions under which a complex algebraic variety, a shape defined by polynomial equations, admits a canonical or most natural metric. Specifically, it concerns the existence of Kähler-Einstein metrics, which are solutions to a version of Einstein's field equations on these abstract spaces. The conjecture proposed a stunning connection. It asserted that the existence of this special geometric object, the metric, was entirely equivalent to a concept from algebra known as K-stability. This algebraic stability is a technical combinatorial condition on the symmetries and singularities of the variety. In essence, a space is geometrically pristine if and only if it is algebraically well behaved. Yau's influence here was foundational, formulating the problem in a way that pointed toward an analytic solution. The path forward involved tackling a formidable complex Monge-Ampere equation, a challenge that would occupy the world's leading geometers for decades. His formulation set the agenda, defining the central problem for a generation of researchers and reinforcing his core belief: the profound truths of geometry are encoded in the behavior of differential equations. His impact was amplified through the creation of an intellectual lineage, a veritable Yau schools of mathematics. Through his decades of teaching and mentorship at institutions like Stanford, Harvard, and the University of California, he supervised over 70 doctoral students, many of whom have become leaders in the field. This prolific advising produced a diaspora of mathematicians trained in his distinctive style, a combination of bold geometric intuition, an encyclopedic knowledge of classical results, and an unwavering command of hard analytic techniques. His students learned to see problems through his eyes, to hunt for the hidden differential equation at the core of a geometric puzzle, and to attack it with relentless analytic power. This propagation of a specific mathematical worldview is a form of influence that echoes far beyond the publication of any single paper. It shapes the very culture of a field, determining which questions are considered important, which methods are deemed powerful, and what constitutes a satisfying answer. Through his students and collaborators, Yau's intellectual DNA became woven into the fabric of contemporary geometry, a legacy of fearless synthesis. To contemplate the full arc of Shing-Tung Yau's career is to witness an exercise in fearless synthesis. His work represents a profound unification of seemingly disparate intellectual domains, a testament to a mind that perceives deep connections where others see boundaries. He dissolved the traditional demarcation between pure geometry and partial differential equations, demonstrating they were two sides of the same coin. The elegant abstract world of manifolds and curvature, he showed, could be explored and conquered with the powerful gritty machinery of analysis. This fusion yielded insights that transformed both fields, providing geometers with unprecedented tools and giving analysts a universe of new, meaningful problems to solve. This synthetic impulse extended directly into the realm of physics. His proof of the positive mass conjecture forged an unbreakable link between the geometry of spacetime, as described by general relativity, and the fundamental physical principle that energy must be positive. He saw in Einstein's equations a source of deep geometric questions and conversely recognized that the pursuit of pure geometric beauty often led directly to results of profound physical significance. This conviction in the ultimate unity of mathematics and the fundamental laws of nature is a modern echo of the Pythagorean faith in a cosmos governed by number. For Yau, this was an active guiding principle, a belief in what Eugene Wigner famously called the unreasonable effectiveness of mathematics in the natural sciences. His career offers a compelling case study, showing that the abstract quest for understanding the nature of shape, when pursued with sufficient vision and technical force, inevitably illuminates the structure of physical reality itself. His life also embodies a powerful synthesis of cultural and intellectual traditions. Rising from humble beginnings in Hong Kong, he navigated and ultimately mastered the highest echelons of the Western academic world. He then dedicated a significant portion of his life to building world-class mathematical institutions in China, working to repay an intellectual and cultural debt. He sought to create a two-way street, fostering a global mathematical community where talent and ideas could flow freely, enriching both Eastern and Western scholarship. He stands as a figure who integrated the rigorous axiomatic traditions of European mathematics with a holistic, intuitive perspective, creating a style that is uniquely his own. The final measure of his legacy resides in the questions he enabled others to ask. His solutions to great problems created entire new landscapes for exploration. The existence of Calabi manifolds opened the door for string theory to become a mathematically coherent enterprise. His work on geometric stability defined a research program that continues to drive complex geometry. He provided the tools, the vision, and in many cases the very language for the next generation of inquiry. Shing-Tung Yau's story is that of a mathematician who was a solver of monumental problems, a builder of enduring institutions, and an architect of new fields of thought. He is a creator of the modern grammar used to conduct our deepest conversations with the mathematical structure of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.